In this video, we will implement a simple Haskell functions which determines the 5 types of binary trees. And let's start from the simplest case. What if they have degenerate tree? So degenerate tree is actually like a list. Okay, let's write function which determine this case. So I will call it deg. And its type signature. It takes some battery of type A and produce Boolean value. What if they have empty tree? If they have empty tree, they can define this as, okay, this is a degenerate tree. But if they have some node, some tree constructed with a node constructor, no matter what the node is, if they have left branch and empty right branch, we can say that yes, it is a degenerate tree, but only if the left subtree is also degenerate tree. Okay, so we solve this as a simple recursion, and also for the right subtree. No matter what the node is, if the left subtree is empty and they have the right subtree, they can say that yes, it is a degenerate tree if the right subtree is also degenerate tree. And this thing should work. I forgot one case. What if they have tree constructed with a node constructor and it has a left and right subtrees? In this case, they can define this as false. This is not a degenerate tree. So now let's check this, how this works. I will load my module here, and if I have some trees like this, and let's check its degeneration or not. Okay, they can see that this is not degenerate tree. But what if I define some tree like this, some degenerate tree? I will start from a node 1, and I have empty left subtree and some not empty right subtree with a node 2 and empty left and right subtrees. Okay, you can see this is a degenerate tree, and now let's check it with our function. They can see that yes, this is a degenerate tree. So they define this case. Now let's check this case, if the tree is full or not full. So the tree is full if every node has only 0 or 2 children. Okay, let's start to define this function. I will call it full, and it has exactly the same type signature. I will take it from here and put it here. And what if they have full tree? Okay, we can say that. What if they have empty tree? Sorry, they can say that in this case this is okay, this is a full tree. And if they have what if they have a tree constructed with a node and it have some left tree and no right tree? In this case, they can define it as false. But what if they have some node here with empty from the left and not empty from the right? In this case, they can say also that this is false. And the last case, if they have node with a left and right subtrees. In this case, they can say that yes, it is a full tree, but only if the also left tree is full and right tree is full. Okay, and this thing should work, I think. Let's try to reload and check this tree. I have some trees here. Tree TR. Actually, it's defined in this model, and this data type is defined like this. So let's check this type of tree. You can see that this is not full tree. Why this is not full tree? It's a full tree. Okay, I think we have some errors here. There is an error. And I think the problem is that in an interesting case here, look, if we have some tree like this, they have some node and empty and empty. And let's check this. Is this full? No. But actually this is full because it have 0 children. But why this happens? This happens because this case put in this pattern and in this pattern. So we catch it in the first pattern. We have some left tree and it is empty, and right tree, this is empty, and the defined it as false. So we need to add some extra case here. Either have some node and boof, or the children's empty. In this case, you can say that yes, this is a full binary tree. And of course, if we have some not empty left tree and empty right, this is not a full tree. And symmetric case, if they have some empty left and not empty right, it always be not empty left and right because the catch the empty case here in this pattern. Now let's try to check this thing. I will reload my module and check for full. Yes, it is full, and our tree is also full. So this is this tree, and you can see it is a full tree. And I also have some complex tree like this. Okay, you can see this is a not full tree, and let's check this. Yes, this is not full tree. Now let's check the balanced tree. Okay, you can see this is a balanced tree. The balanced tree is tree in which the left and right subtrees are differ in height at most 1. Okay, and of course this constraint is holds for every node of the tree. So we can see this definition here. Okay, let's define this function. I will call it balanced and type signature exactly same. So if we have empty tree, we can say that this is okay, this is a balanced tree. But if we have some node and left and right subtree, according to definition, we need to say that this is absolute value of the height of the left and height of the right is less than or equal 1. Okay? And also I need to check if the left also balanced and right also balanced. Okay. So these constraints must hold for left and right subtrees. Of course, we need to define the height function here. And to do this, this is a very simple. The height function, it takes some binary tree of type A and produce integer, the height of this tree. And for the simple case that they have empty tree, we can say that its height is 0. But if we have left and right subtrees, we can say that the height of this tree is 1 plus maximum of the heights of the left and right subtrees. Okay. So the recursive definition, simple recursive definition, will give us the height of any binary tree. Now let's try to check this solution. I will reload and let's check the balance of this tree. So they have this tree and balanced tree. Yes, it's balanced. And also they have this tree. You can see it's not balanced. Let's check this. Yes, it's not balanced. And now let's check the tree is perfect or not. So this is a perfect tree. So what is a perfect tree definition? A perfect binary tree. A binary tree is perfect binary tree in which all internal nodes have two children and all lives at the same level. So you can see here all internal nodes have two children and all lives at the same level, and such tree is a perfect binary tree. You can see that any perfect tree is complete binary tree, but the complete binary tree is not necessarily a perfect binary tree. Okay, now let's go to our implementation and implement the function which check if a tree is a perfect binary tree or not. Okay. Okay, let's call our function perfect and type signature we take from here. If we have empty tree, this means that our tree is perfect. But what if we have tree, some tree t? Okay. How can we define the tree is perfect or not? So we have some leaves and every leaf on the same level. So if we take the height of the tree and then we count all the nodes in the tree, we can see that exists a relation between the height of the tree and all the nodes in the perfect tree. And what is this relation? Okay, look at this example of the perfect binary tree. It has length the length 3, and it has 7 nodes. If let's count this number of nodes, here they have 7 nodes. And height is 3. So we can see that at the first level they have 1 node, at the second 2 nodes, at the third they have 4 nodes. So this means that at every level the number of nodes increased by 2. Okay, so we need to multiply every previous number on the previous the number of nodes on the previous level by 2 to get the number on the next level. So this means that we have some geometric series here, but in Haskell we can sum this geometric series. Okay, so I can say that my tree is perfect if the count, so the number of the elements, is equal to some number which I can derive from the height of the tree. So if I take the list from 0 to height of the tree and then fmap this list with power 2 function, okay, I will get the geometric series. And now I can summarize them. So if this relation holds, then I can say that this is a perfect tree. Of course, now I need to define this count function and height. And let's do this. I can say that that our height is the height of the tree minus 1. And I can say that our count function, so I need some count function here. And to implement the count function, this is very simple. We can take this type signature from here. Of course, if the tree is empty, we can say that it has 0 nodes, but so it's like height definition, but we need to change this name to count, and we need just recursively count the nodes in the left and right subtrees. So this function works exactly like this. And let's try to reload. Okay, you can see that it's reload. We have some tree. And now let's check perfect it or not. Yes, you can see that this is perfect, and this tree complex, for example, it's not perfect. Okay. And also we can see what they use the geometric series here, and they can use this formula to make our function much faster without using some function. So I write this formula here, and they need to change this sum. Okay, let's define it like S, and and do some definitions as equal to this. I think this should works, and I just redefine this S as okay. What our B1 in geometric series? We start from 1, I think. Yes, the first element. So let's look at this. For example, for tree with the height 3, we start from 1, and then we have 2 nodes on the second level. On the third level, we have 4 nodes, and on the level number 4, we have 8 nodes. And we need to summarize this thing. This is a geometric series. The first element B1 is equal to 1, and then we need to take our Q, and our Q is 2, and we need to use our height here. So the height is defined like this, and we need to divide this thing. Okay, we need to divide it by 1 minus 2. Okay. So let's try to evaluate this expression. This is some height 3. You can see they have 7 here, but I don't want to have a floating point here. I want to use integer. Okay, let's try to use div for this. I think div should work. Yes, it works. So if I define this like this thing should work, I think. Let's try to reload and check. It doesn't work for this tree. Start. This means that I broke something. So I have this tree, and it tells me that it's not perfect. And I think the problem here is that I need to remove this -1 here, because I use list here. Okay, and list is started from 0. So let's check now. Perfect tree. Yes, now it works. Okay. Let's do this -1 here. And let's check this type of definition. Yes, it works. So I state like this. I think it's faster. And now we will check the last type of tree. It's complete tree. So the complete tree is like perfect tree, but the last level, where all the leaves of this tree is possibly not filled to the end. Okay, you can see this definition here. Okay, and now let's do the implementation. To implement this function, we can use the fact that in a complete binary tree, the tree of height, the maximum height minus 1 is a perfect tree. Okay, this is a perfect tree. And this means they can use that perfect binary tree function which we already implement. So we will take some tree, take the level, take the height, take its height, and subtract 1 from this height, and they need to check that the number of nodes of this tree without leaves is equal to geometric series, okay, of height minus 1. So we need only to implement one function which count the nodes, all the nodes except leaves. Okay, let's start. I will take this definition of the perfect tree, copy it, and define this function as complete. But I need to change something. So here we need to count except leaves, and I will change the function here. And also we need to take not all the height of the tree. We doesn't need a last level. So the height is minus 1 here. So we have this number of nodes in a subtree. This relation to the height minus 1 is this. And now we need to implement the count, this count function. So it will be implemented exactly as this function here. But we need to skip the leaves. How can they skip the leaves? So to skip the leaves, we actually need to add one extra condition here. Then they have the leaf. This means the empty. The left subtree is empty, and the right subtree also is empty. And in this case, they need to define it as 0, because leaf doesn't get any meaning to us. So, and let's check this function. So if I have this tree and I need to count all nodes except the leaves, it takes me 7. Why? Of course it takes me 7 because I don't rename this thing here. Yes, it gives me 3. So for this tree it gives me 3 because I don't count these leaves. So actually I can check now this tree for completeness. Let's try. You can see, yes, it is complete tree. But what if I have some another tree like this? Like this. So this is not complete tree. Let's check this. Yes, it's not complete tree, but let's create some new tree like this. I think if I have root node, and some empty left and some right subtree without any continuation. So this is also a complete tree. And now let's try to check this. Yes, you can see that this works as expected. So this function bridge will check if the tree is complete or not. So guys, thanks for watching. You can find this code in the links in description to my Gist repository. And push like, push subscribe button, write comments, and see you in the next video. Bye bye.